Well, let's see if I can stir up a little bit of controversy with this then. Before I start this talk, though, I just want to thank Mikhail for inviting me in as a author to this book, as a joint author to this book. Although a lot of the credit for this, putting this whole thing together goes to Mikhail, and also thank my other co-authors as well for what's been a great experience. Today, I'm just picking on magmatism in transform and continental strike slip settings as one aspect of what's covered in the book. And you might think that magmatism is, those of you who are working on in industry, for example, well, what's magmatism got to do with me? Why is it important to what I'm working on? But it turns out it actually is quite important. Here's just a few examples, practical reasons why strike slip magmatism might be important. First and foremost, those who are working in still working in offshore oil and gas exploration must know that a lot of the deep water exploration that's taking place nowadays is in continental margins that are affected by magmatism. Just two examples shown here: the Norwegian Barents Sea and the offshore Guyana Suriname, where we have strike slip, we have continental margin, and we have magmatic edifices. From a geothermal point of view, strike slips pretty important, or can be pretty important. One of the, I guess, top areas in the world for geothermal energy, a country that's powered by geothermal energy, Iceland. The geothermal centers in this area along here, the Reykjanes Peninsula, are basically associated with a major strike slip zone and are centered in fissure swarms, which are conjugate faults along this strike slip system. And then last but not least, volcanic hazards on the right-hand side here. This is just an example from California, which I'll come back to later, the Walker Lane. And here we have a diffuse dextral strike slip system with some very large calderas, including some volcanoes which are regarded as present active and quite dangerous, like the Long Valley caldera along the length, so volcanic hazards as well. And then, some other things that I could mention: fluid flow, basal heat flow, mineralization. There's lots of reasons why the association between magmatism and strike slip could be important. Now, there's talk of heat flow, of thermal variations of magmatism all the way through the book. But these five categories are the ones to particularly considered. And of those, I just want to pick on these, and I'll detail these later. The big effects, basically plate boundary effects, magmatism at transformers, both continental and oceanic. So here's a starting position and a hypothesis. Transform faults basically express plate motions. They're often non-Andersonian. I've put that in inverted commas because strictly they may be a special case of Andersonian faulting, but in the case of oceanic transforms, you actually see often don't see the usual phenomena associated with strike slip faults, the conjugate shears, radial shears, and so on. Transforms cut the whole lithosphere by definition. They are basically motions between plates, and they're subvertical shears. Now, that doesn't mean to say they're a straight line all the way down to the mantle. They may anastomose, they may be affected by the different rheologies that they go through, but essentially they're subvertical. So following on from that, you would think that transforms should be able to form conduits for magma from mantle depths and possibly produce excess magmatism at plate boundaries. And this little illustration here, we're showing typical upwelling of a asthenosphere at a mid-ocean ridge with fractionation and mid-ocean ridge basalts coming out. Then in the case of a leaky transform, you have a direct line essentially into the mantle where you may be able to get more primitive melts, and I'll say more about that later. So here are some typical transform habitats. Very diagrammatic, but so we can talk about continental transforms, examples that Mikhail showed earlier. We can talk about continent-ocean interactions, in other words, transform margins, or in this case here, an inherited transform, a transform that's been reactivated as an ocean. And finally, in the oceanic domain, we have the rather unique oceanic transform faults. And of course, as you know about these, essentially the active portion is between the segments of the spreading ridges. The inactive portion are called fracture zones. And the odd thing about oceanic transform zones is that the offset of the ridge is in the opposite sense to the essential motion along the transform zone. So, for example, the motion along this transform is sinistral, but the ridge is offset dextrally. Now, if we wanted to make these magmatic, well, one way we could do it is we can just heat them up. We basically have a source of heat from underneath, let's say from a hot spot or a mantle plume, and any of these environments can then display excess magmatism. In fact, I'd go further than that. Any geological environment in the world can have excess magmatism if you have a hot spot underneath. And of course, there's a lot of literature on the interaction of ridges or transforms with a hotspot. Here's a couple of examples. The left-hand side one is from the Marion and Bouvet hotspots, which are south of Africa. Basically, these people diagrammatically here are showing how offset ridge transform systems might interact with a hotspot or mantle plume, and how the transform fault in itself may form a barrier to flow of material from the hotspot or mantle plume and limit and control the extent of the hotspot effect in terms of excess magmatism. The right-hand side is the most famous example of hotspot ridge interactions. This is Iceland. In the case of Iceland here, and Mikael showed you some examples from this earlier, the spreading ridges in the adjacent North Atlantic, the Reykjanes and the Kolbeinsey Ridge, are offset towards the position of the current hotspot by strike slip zones, the Southern Island seismic zone here in the south, and the Tjørnes fracture zone up here in the north. So basically, we've got we seem to have strike slip zones which are affected by the action of the hotspot, but at the same time, the conjugate shears and so on of these strike slip systems form conduits for lavas. So it's a two-way process here. So lots and lots of study of places where we have strike slip in association with a hotspot. But what about cases where there is no hotspot? Can we still have magmatism? Well, it turns out, yes, we can. There's lots of examples worldwide. And in this, I've gone back to those transform habitats I talked about earlier. And I've said, okay, first of all, why would we get magmatism at a position like this? And then some examples of where you see this. And you can see there's lots of these worldwide. But so instead of going through all these words and reading them out here, I just want to draw your attention to one common factor here. In the case of all of these different habitats, the common factor is divergence. In other words, an extensional component or a divergent component across the transform, which allows that subvertical shear to open and admit magmas from depth. And these are one great example of where this happens is in the case of leaky transforms. And leaky transforms basically means that they produce magmatism, excess magmatism along their length. And you can see these in both the continental domain and in the oceanic domain. So on the left-hand side here, we can see the Dead Sea Fault, which is a large sinistral strike slip system, which basically accommodates motion of the Arabian Plate northwards as it crashes essentially into the Zagros mountain belt. And all the way along here, we can see, like a string of pearls, magmatic centers, neogene magmatic centers associated with the present-day active motion of that fault. And these usually occur at pull-apart basins, at places where you have stepovers and pull-aparts. There's other magmatism in the area, but that's possibly hotspot related and not related to the Dead Sea volcanic centers. Then in the oceanic domain, there are lots of examples of leaky transforms. This is a particularly prominent one on the right-hand side here in south of New Zealand. This is the Emerald Transform, where basically there's been a change in the plate motion. The original transform fault has broken up into a series of offset ridge segments and mini transforms, pull-apart basins, forming this big welt and the formation of volcanic centers in the strike slip zone. Now, in this particular case here, the authors of this paper that I've taken this from say, well, some of this volcanism, this excess volcanism here, might be due to the activity or the influence of a nearby hotspot. So, okay, we're back to this thing of is the excess magnetism imposed by an outside agency, or is it caused by the transform itself? So here's an example where there is no known hotspot nearby. This is another series of leaky transforms, and this is to the west of Central America. We've got the East Pacific Rise, which is a fast-spreading ridge in this area. And this is the Clipperton and Siqueiros transform faults. And here, a counterclockwise rotation in the plate motion just a few million years ago essentially turned what was a straightforward transform into a rather complex structure. So along the Clipperton transform, we can see compressional features along its length, forming this sort of compressional welt. But perhaps more interesting, along the Siqueiros transform, which steps in an opposite direction, we can see the development of offset ridges, pull-apart basins, and lots of volcanic edifices in this area. And this volcanism has been sampled. It's primitive magma, it's picritic, it seems to be coming from a deep position as opposed to the mid-ocean ridges nearby, which are these spreading centers essentially show normal fractionated mid-ocean ridge basalts. And you can see in at least one example worldwide, there may be more, I don't know, a fossil leaky oceanic transform. As you probably know, in Cyprus, you've got an abducted lump of oceanic crust, the Troodos Massif, and the Arachipus fault in this area appears to be a fossil leaky transform. And why do we know it's a leaky transform? Well, we've got the same feature taking place in this area. We've got mantle rocks in the fault zone, and also picritic dikes of deep origin. So this is basically a fossil example of what we saw there in the Siqueiros and Clipperton transforms. And so going to the continental domain for a little while here, I showed you a clip from this earlier. This is the Gulf of California, of course, and along as you know, the Gulf of California, the Pacific spreading ridge enters into the Gulf through a series of segmented and offset transform sections with dextral motion, and a large number of pull-apart basins along this line. And some of these pull-apart basins, going back to what Mikhail said, evolved very quickly into spreading centers just over a period of a few million years. For example, the Guianas Basin here turned from a pull-apart basin into a little mini ocean with excess magmatism within about 6 million years. In this area here, we've got a strong magmatic buildup, and again, these lavas are picritic, primitive, coming from depth. Then if we move northwards into California, Nevada, a lot of the right lateral motion is taken along the San Andreas fault zone, of course, but the actual plate boundary is along the Walker Ridge, which I mentioned earlier, where we see numerous step-overs, pull-apart basins, and so on. And most importantly, some major volcanic centers all the way along this area. No hot spot in this area, and no subduction in this area. Subduction is taking place further north in the Cascades, but probably a thermally weakened crust here from preceding episodes of subduction, which allows these major volcanic centers to form along the transform. So looking at transform margins themselves, which Mikhail spent quite a lot of his talk talking about. Here's a couple of examples of some of the major examples of transform margins in the world. And I've shown these two examples here, the De Geer transform and the equatorial transform, because these are essentially very different in character. The De Geer transform is strongly magmatic. The equatorial transform does have some excess magmatism along its length, but generally speaking, it's weakly magmatic. So Why is that? Could it be due to, if we're looking for hotspot type explanations, could it be distance to hotspots? Well, the equatorial transform is actually 600, 700 kilometers away from a couple of active hotspots. The Dore transform is 1,600 kilometers away from that hotspot that we saw earlier on in Iceland. So in many ways, it should be the other way around, but it's not. The answer may well be in the obliquity. The obliquity of the transform motion in the case of the Dore is 30 degrees or more. The obliquity in the case of the equatorial transform is less, it's 10 to 20 degrees. So the divergence along this line here will be greater. The Dore, I think, is a fairly undisputed example of oblique opening along a continental transform. In this particular case, opening of the Northeast Atlantic is relayed into the Arctic Ocean, into the Eurasia Basin, along this what started as a continental transform motion and evolved into a continent-ocean transform, with a divergence angle of about 30 degrees, as shown earlier. And very early on in this opening motion, looking at the right here, we saw the development of a major pull-apart basin, the Sylvester Nugget Basin, Vestbakken Volcanic Province, and saw the development of this very early on in the Eocene. While this was happening, though, while this was all opening in the south and divergent, there was extreme transpression taking place in the north, forming a fold and thrust belt in Spitsbergen. So this is a diagram basically showing the evolution of the ocean in this area, and I won't go through all of this, but I'll say that at the bottom right here, we see the Vestbakken Volcanic Province, that pull-apart basin that I mentioned earlier. This is highly volcanic. There are seaward dipping reflectors in its north. There are lava flows, there are sills, and there are actual volcanic centers. And there appear to be two ages of volcanism in this area, Eocene, early Eocene, and early Oligocene. And that they may well be because of the initial pull-apart basin, initial development of the pull-apart basin, and then later on, as the ridge passed along the margin past this Vestbakken province, again, the ridge passage may be responsible for the second episode. I want to finish up then by talking about one of the last transform habitat. And I wanted to ask what would happen if a continental transform, basically the boundary between two continental plates, was inherited as an orthogonal transform, was exploited to form an ocean. Now, early on, I've been talking about divergence and how an extensional component across the transform may well be a recipe for magmatism. And if that's the case, in pull-apart basins, leaky transforms, and so on, if that's the case, this should certainly be a candidate, since we're seeing rather immediate divergence across a continental transform. But do these actually exist anywhere in the world? Well, it turns out there's some pretty good examples of places where they exist, and probably the best one of all is the Central Atlantic. As you know, the Central Atlantic opened and closed several times. That's the story that's basically told, and people think of it as like a concertina going in and out. It wasn't like that. In the end of the Carboniferous, beginning of the Permian, there was a huge dextral component as these two continental plates collided, 1,000-kilometer scale dextral motion between the plates. Then when they open, this is the situation we see. We see a rather thick continent going into oceanic crust in almost no distance, over a distance of about 20 kilometers. Very little preceding observable extension. And this is a magmatic margin. So this begs the question, are we actually looking at opening along a transform in this area? And here's the general idea. So if you have a steep weakness in the lithosphere and you open it, you should have an area of thick lithosphere against upwelling asthenosphere, large lateral temperature gradients, with the possibility of a upwelling system, of a convective system developing, and a zone of melting. This isn't a new idea. It was suggested back in 1988 by Mutter, but it didn't catch on at the time. I'm suggesting here that this idea could be revitalized. On the right-hand side, I show different types of divergent continental margin. And what I want you to note here is the at least superficial similarity between a magma-rich margin and a transform margin. Both show an abrupt change from continental to oceanic, as compared to the more gradually thinning magma pore margin, where we see the usual necking, stretching and thinning and so on, until eventually you have oceanic crust. So basically, that's great as a theory. It should, there should be some truth in it, but the question is, can we actually simulate magmatic margin geometry by exploiting a transform, and can we produce enough magma? So we tested this, and this didn't make the book that we're talking about today, because it was still in process during when the book deadline came along. But so we took this idea basically of what happens if you actually change the plate motion and pull a transform apart. Would you set up this convective system, and would you actually simulate a magma-rich margin? And we modeled this on the computer using reasonable values for crustal and lithosphere temperature and rheologies and so on. And the bottom line from this initial model, at least, is that we found we could fairly well simulate the abrupt continental margins, and more importantly, we could simulate the rising of the geotherms, which are shown here in white, which, if this actually happened in reality, would actually cause magmatism. So the postulate here is, yes, there may be many magmatic margins worldwide that are due to external agents, such as a hotspot, but maybe in some cases there are other reasons why you can get a magma-rich margin. If you want to read about this, this is in another of Michal's books, which was published in 2022, a geological special publication 524. So just finally, a few takeaways from my section of this presentation. There's globally abundant evidence for magmatic involvement in strike slip and transforms, often not involving external agencies such as hotspots. Transforms cut the lithosphere and should form avenues for sublithospheric melts. Leaky transforms, continental and oceanic, provide the most definitive evidence of this happening. All of the examples include a divergent component: offsets and pull aparts, oblique transform margins, rotation pole changes, as in oceanic leaky transforms. And then, more speculatively, the continental transforms may predispose magma-rich divergent margins. And for that, there's regional evidence that there was a transform there in the first place, the abrupt and the linear margins, and the minor extension preceding breakup. And the initial computer modeling at least supports this concept. So with that, I will end my talk, and I take any questions or take them at the end as you wish. Thank you very much.